Hello, thank you for watching this video. So in this video, we're doing question 10 of May June 2022 question paper mathematics paper 2. And the topic is Euclidean geometry, which will maybe discuss proportionality and similarity and all other Euclid principles or geometry principles. So let's go. At 10.1, they're saying in the diagram, triangle ABC and triangle DEF are drawn such that angle A is equal to angle D, angle B is equal to angle E, and angle C is equal to angle F. So they're saying use the diagram in the answer book to prove the theorem which states that if two triangles are equiangular, then the corresponding sides are in proportion. So here's what we have here. We have triangle ABC, right? And triangle DEF. So they have told us that these two triangles are drawn such that this angle is equal to this one, this angle is equal to this one, and this angle is equal to this one. So these two triangles are equiangular because the corresponding angles, all the corresponding angles of these two triangles are equal, right? Because you are given that A is equal to D, B is equal to E, and C is equal to F. So these two triangles are equiangular, which is the corresponding angles of these two triangles are equal in measure, right? So they want us to use the answer book to prove the theorem which states that if two triangles are equiangular, then the corresponding sides are in proportion. So they want us to prove the theorem which states that since these two triangles are equiangular, which is they have equal corresponding angles, we must show that the ratio of the corresponding sides are equal. That's what they want us to do. We must show that the ratio of the corresponding angles so they want us to show that the ratio of the corresponding sides are equal. So in this case, you can see that AB over DE. That's the one that we can show. Your AB over DE is equal to AC over DF. You don't necessarily have to prove this one. You could also show that your AC over DF is equal to BC over EF. Or maybe your EC, or maybe your BC over EF is equal to your AB over DE. Any of those ratios, it should work, right? No problem. And also, I would say this is this proof that they expect you to do here is similar to the one that says that if two triangles are equiangular, all the corresponding sides are equal in measure. It is the same theorem. But in this case, you don't have to show all the corresponding sides. You can just show one, which is what they wanted you to do. So they don't want you to show that the ratio of all the corresponding sides are going to be equal in measure. You can just show just two, which is this what they asked you to do here, and you'll be fine. So let's go. So how are we going to do this? So we have to make some construction. Because we want to show that the ratio of the side to that side equal to the ratio of the side to this side. So we have to do some constructions and do business. So let's get started. So this is our proof that we're going to do here. So I'm going to start with some constructions. So what are we going to do? I'm going to mark point X and Y on line or maybe side AB and AC respectively, so that your AX is equal to DE and your AY is equal to DF. What is this? So what I'm saying is I'm going to mark point X and point Y on sides A and C respectively. So what does this mean? I'm going to mark point X on line AB and mark point Y on side or line AC, so that your AX, right? So I'm going to mark point X here on this line, and I'm going to mark point Y on this line, so that this side here is equal to this side, and the side over here is equal to that side over there, right? The next thing that I'm going to do is join XY. So next thing on my construction, I'm going to join XY. So I'm going to join XY, which is these 2 points over here. I'm going to join these 2 points over here, XY. So what I have a triangle that looks like this one, right? Because look, this side is called this side, this angle is this angle, and this side is that side. So what I'm going to do first, I'm going to show that these two triangles are identical, which this is the same triangle, but they're just named differently. So how am I going to do that? I'm going to prove that these two triangles are congruent, which is they're identical. That's what I'm going to do. After showing that these two are identical, which is this side is equal to this side, right? This angle here is equal to this angle, and this angle will be equal to that angle. That's what I will have done. Because it's clear that this side is this one by construction, and this side is this side because we're given that, and this side is equal to that side by construction. So by congruence, we're going to show that these two sides are equal, and this angle, or these two correspondings, are also equal in measure. So what I'm going to say now, I'm going to say in triangle. In triangle what? In triangle AXY, right? In triangle AXY, triangle AXY, and triangle DEF, and triangle DEF. So I'm looking at these two triangles. So I'm going to say, let's say maybe this is X1 here, and this is X2, Y1 and Y2. So these two triangles, I'm going to say AX is equal to DE. So our AX is equal to DE by construction. So I'm going to say, okay, side AX is equal to DE, because that's how I've constructed this triangle, these two sides. So we constructed such that these two are equal. So your AX is equal to DE by construction. Right? No problem. Next, angle OA, this angle A of this triangle over here, angle O, is equal to angle D. We're given that because it is. So our angle A is called angle D. This was given information. Right? And our AY is equal to DF. That is part of my construction as well, because I've constructed AY, so that is equal to DF. So I'm going to say our AY equal to DF by construction. So in that case, we can say, therefore, these two triangles, which is triangle AXY, is congruent, which is identical, or these two triangles are the same. This triangle AXY is the same as triangle DEF. One of the criteria that I use is side angle side. So if you go to my playlists and watch my bed action sessions, I do have bed action sessions. I did teach congruence. I did explain congruence there. So if you can go there, you will understand what this thing means, what congruence means if you don't know what it means. So in that case, these two triangles, this triangle and that triangle, are identical. So in that case, look, if these two triangles are identical, this A is D, X is E, and Y is F. So which means, if we say this side is that measure there, this side should have the same measure. This F should be the same as that one, right? So in that case, we can say our angle X1 is the same as angle E, because these are the same side, these are same angles of congruent triangle. So you're looking at the same angle of identical triangles. So what I'm going to say, I'll say, okay, look, angle X1 is equal to angle E. Why? These are corresponding angles of congruent triangles. So you are looking at the same angle of identical triangles. So these angles are equal. Look now, your angle E is equal to x1 and your same angle E is equal to B, you are given up there. So you say now, look at your angle E is also equal to B, right? So you are given this information on a statement that these two angles are equal. So if your angle x1 is called angle E and your angle B is called angle A, it's obvious to me that these two should also be equal because they're both equal to the same thing. So your angle x1 is equal to angle B, right? So which means, look, this angle here is equal to this angle and this angle is equal to this angle. So these two angles are also equal. So if these two angles are also equal, what does it mean? These angles are corresponding angles, right? Because look, they are sitting in the same position in relation to their lines and this common line that they are sharing. So this line XY and this line BC, right? They are both intersecting the line segment AB at point X and B. And they intersected at the same angle, which means you have two lines that intersect the common line, which is the transversal AB, at the exact same angle. So these are corresponding angles. And those corresponding angles of yours are equal in measure. So if your corresponding angles are equal in measure, which means those two lines are parallel. So because your corresponding angles are equal, it means your line XY and your line BC are going to be equal in measure, or are equal in measure. So in this case, I'm going to say, therefore, angle what? Oh, XY is parallel to BC. Why? Because these two corresponding angles are equal in measure. Because the corresponding angles are equal in measure. Because you have two lines, XY and BC, both intersecting the same line AB, which is a transversal AB, at the same angle, which means they should be having the exact same orientation. Therefore, they are parallel. So these two are parallel. So we can add that information. Okay, and say, okay, this is parallel to this. So since these two are parallel now, let's look at triangle AXY and triangle ABC. You can see that triangle ABC is divided by XY, which is parallel to the third side. Right? What does that mean? You might remember your proportionality theorem. It says that if you have a triangle ABC and the triangle ABC is divided by a line segment XY that is parallel to the third side, then it will divide your two sides proportional, which is at the same ratio. That's what the proportionality theorem says. It says if you have triangle ABC and it's divided by XY, which is parallel to the third side, then that XY will divide the two sides of that triangle at the same proportions or at equal ratios. Right? So in that case, we can say if you take your AB, right, over your AX, it should be the same as AC over AY. That's what that means. So in this case, what do we say? We'll say, okay, in triangle ABC and triangle AXY. So if you look at this triangle ABC and triangle AXY, what we will say is if we take our AB and divide it by our AX, it should be equal to AC over AY. We're applying what? We're applying the proportionality theorem here. Why are we applying the proportionality theorem? Why it works? Because the XY is parallel to BC. Let me repeat it again. I'm saying that you have triangle ABC, and ABC, two sides of a triangle ABC are joined by line XY, and your line XY is parallel to the third side. It's joining two sides and parallel to the third side. So it will divide the two sides at the same ratios or at equal proportions. So in that case, your AB over AX should be the same as AC over AY, as long as you take the ratio of the same parts. They should come out the same. Even if you say AX over A, or AX over XB is the same as AY over AC, or maybe XB over AB should be YC over AC. As long as you are consistent in taking the ratios of the same parts, or the same parts, yes, the ratio should be the same. But look now, remember that by our construction, we said that AX is equal to DE, right? And we said that AY is equal to DF. So, which means this AX is the same as DE, and that AY is the same as DF. So in that case, what we will say is, therefore, AB over AX, our AX is the same as DE, is equal to AC over AY. What is our AY? Our AY, by our construction, is the same as DF, which is what we wanted to prove to begin with. Right? So, this, we have shown that if, in this case, we have shown that if two triangles are equiangular, right, the corresponding sides are going to be in proportion, right? Which is the ratios of the corresponding sides are going to be equal. So, but you've only shown this for one side. So you can stop here because that's what they hinted you to do here. But if you want to prove that if two triangles are if you want to show that two equiangular triangles are similar, you have to show all of those ratios, which is you must do the same thing for these two and do the same thing with all those two as well, so that they are all equal. So in this case, you will stop here to this question, right? Because this is what they wanted of you. This is what they asked of you. So if maybe you wanted to show all three, you're going to have maybe a similar construction to this, but maybe let's say you have another construction like that there. So that this side maybe is equal to this side, and this side is equal to this side, and this side is equal to this side, and apply the same steps. So, which means maybe say this is K and say this is L. So that this side here is equal to that side, and this side here is equal to maybe this one over here. Right? So, in this case, and show that these two triangles are also congruent, the same we did here. Because this side is going to be the side is going to be the side, that angle will be the side, the side angle side. And do the same thing. You will find out that the ratio of maybe AC over KC, the same as that of BC over LC. Right? And then do the same thing. Similar way. If this entire side over this is equal to this entire side over this, and this entire side over this, or this entire side over this is the same as this entire side over that, which means these two are also going to be equal. But we don't have to show all two of them. This ends here for now, so I'm going to end there. And I hope it does make sense to you as it does to me. So what I'm going to do right now, I'm going to clean the board, and we're going to do question 10.2. So let's clean the board and do question 10.2. Okay, so now we're doing 10.2. At 10.2, they're saying, in the diagram, O is the center of a circle passing through A, B, C, and D. EC is a tangent to the circle HC. Diameter AB produced meets tangent EC at E. F is a point on EC such that BF is parallel to EC. Radius CO produced bisects AD at G. BC and CD are drawn. So that's in this diagram, right? O is the center of the circle. So this is our center of the circle. A, B, C, and D are points on the circumference of the circle, right? They went on to say that EC is a tangent to the circle at C. So there is your EC. EC is a tangent to the circle, right? No problem. They went on to say that diameter DB produced intersects tangent EC at E. So you have a diameter that is DB, right? And this diameter of yours intersects this tangent at point E, right? they went on to say that F is a point on EC such that BF is parallel. F is a point on EC such that BF is perpendicular to EC. So they are saying that F is a point on EC such that this line BF is perpendicular. This line BF is perpendicular to EC. And they went on to say that your radius CO extended to G bisects this chord. So let's have a closer look. So you have A, B, C, and D. They are points on the circumference of this circle. O is the center, right? No problem. So BD is a diameter. What is a diameter? A diameter is a special chord that passes through the center. So DB is the diameter. And this DB of yours is extended so that it meets the tangent EC at point E. So what is a tangent? Here's our tangent EC. A tangent is a line that touches your circle at one point. So which means this line EC only touches this circle at point E. So it is a tangent, right? No problem. And they went on to say that you have a point F so that you have a point F on this EC so that FB is perpendicular to EC. And you have your radius CO extended to intersect our chord AD at point G such that the extension of CO meets G at the meet AD at the midpoint, which is G. So what are the importance of these things? So EC is a tangent, right? EC is a tangent. Let me make it a bit red. EC is a tangent. What is the significance of a tangent? What does it tell you? So you must remember when you're doing tangents, go to my playlist and watch my bed action. I did the tangents, right? I said that there was a theorem called the tan chord theorem there. The tan chord theorem, it was saying the angle between the tangent and the chord is equal to the angle that that chord will subtend on the other side. So if you're saying this EC is a tangent, you can see that your EC meets a chord here, like this chord BC. And this chord BC subtends angle D, right? So which means this angle over here should be equal to angle D. Because the angle between the chord, the tangent, right, and the chord will be equal to the angle that this chord subtends on the other side. Right? So in a similar way, if you were to look maybe at this entire angle over here, this is the angle, or actually this is not a chord, no, so it will not work. No, because this is the tangent over here. This is a tangent EC, and it intersects the chord CB. So the angle between the tangent EC and chord CB will be equal to the angle that this chord will subtend on the other side. So this angle and that angle are exactly equal. It's the same angle. So I can say the angle between the tangent and this will be equal to that one over there, because CG is not a chord. It only works if the angle between a tangent and a chord. That's what the diameter has told you, that these two angles are going to be equal in measure. What else did they say? They say that we have a diameter dB. So where's our diameter dB? Our diameter is this one over here. This is our diameter dB. What is a diameter? You know, a diameter is a chord, special chord that passes through the center. So this is a chord, right? dB. And it passes through the center, O. So what do you know about diameters? You know that diameters, they subtend 90-degree angles. So, which means if this is a diameter, so the angle formed by this diameter here should be 90. So this angle over here should be 90. Because the angle is subtended. It's an angle that is formed by a diameter. You know that your diameter, they form 90-degree angles. So this is 90 degrees over here. No problem. Because when you're reading a statement, it tells you these diameters, the tangent and stuff. Those words mean something, which is this. So that is how you break down these kind of questions. What does it mean to be a diameter? It means, okay, it's a special chord that passes through the center and it subtends 90 degrees. Go look for all the angles that are subtended by the diameters. What does it mean? What does it mean to be a tangent? Tangent is a line that touches your circle at one point. Fine. What does that tell you? What do you know about tangents? You know that the angle between tangent, right, and the chord would be equal to the angle that this chord subtends on the other side. And the angle between the tangent maybe and the radius should be 90 degrees. So in this case, if you're saying EC is a tangent, and you can see your CO is a radius. So the angle here, this angle over here, I'll make it red. This angle over here should also be 90 degrees as well. Because this is a tangent and this is the radius CO. So the angle between the tangent and the radius should be a 90-degree angle. That's what we did when we were doing bad actions. Go to my playlist and watch tangents. Then you'll get to understand that. So these kind of information, this kind of information is important, right? Because once you know the meaning of words and the implications, it's easy. Once you feel this, it will be easy to answer this question. And also, we are told that this is a radius that has been extended to meet AD at the midpoint G. So that's saying this is G is a midpoint, right? And you know, theorem, one of the first theorems, or theorem 1b, it says that a line from center to a midpoint chord is perpendicular to a chord. So this angle over here should be 90, this angle over here. So a line from center of the circle to a midpoint of a chord is perpendicular to that chord. That's theorem 1b. If you watch my videos, that's how I numbered it. If you watch my bad actions, this is theorem 1b, this angle should be 90 degrees. Once you understand and you fill out this information, all the questions will just follow easily. So let's go. At 10.2.1, they are saying prove with reasons that FB is parallel to CG. So they want us to prove that FB, which is this line over here, is parallel to CG, which is parallel to this line over here. This is what they want us to prove. This line is parallel to that one. That's how they want us to prove. So this is 10.2.1a. 10.2.1a. So they're saying show or prove that FB is parallel to CG. So how do you prove that two lines are parallel? So from my bad actions, I taught you 3 ways. 1, show that the corresponding angles are equal, if there are any. The co-interior angles are supplementary, or the alternate angles are equal. If you can show those, that will be enough to show that 2 lines are parallel. But now, if you have done proportionality as well, you can show that if this applies as well, you can show the converse of the proportionality theorem, that if you have a line segment that divides 2 of your sides proportionally, then that line would be parallel to the third side. That's another way. So in this case, we're trying to show that this line is parallel to that one. It's either we can show the corresponding angles are equal, the co-interior angles are supplementary, or the alternate angles are equal. So how are we going to go about this? So look, this angle over here is 90 degrees F1, and this angle here is 90 degrees. This right angle here. This right angle were not given. We said ourselves that there will be 90 here, because this is the tangent and this is the radius. So there's a 90 there and there's a 90 here. So, and these angles are sitting at the same position in relation to the transversal, which means you have 2 lines, FB and CG, that are intersecting. A common line is C, and that intersecting that line at the exact same angle. So what does that mean? It means these 2 lines have the same orientation, therefore they are parallel. So what you need to show, that this angle and that angle, which is the corresponding angles, are equal. Then you're done. Or if this is 90 and so is this one, so if you add these 2, they will give you 180, which is the co-interior angle supplementary. Any of the 2 is enough. So in this case, what I will say is, okay, look, I'll say angle F1, it's called 90 degrees, right? Why? This was given information, right? And on the second one, I'm going to say C1 and C2, they make 90 degrees. C1 and C2, They make 90 degrees. Why? Because our radius, which is CO, is perpendicular to a tangent, which is EC. I taught this on my directions. So therefore, F1 is equal to C1 plus C2, which is this angle here is equal to this angle over here, C1 and C2. Right? We can say therefore, your FB is parallel to CG. Why? Because the corresponding angles are equal. That's one way to go about it. And we have done with 10.2.1a. So we move to 10.2.1b. That's all we are. So let's do 10.2.1b. What are they saying? They are saying, prove with reasons that triangle FCB is similar to triangle CDB. So they want us to show that triangle FC Barcelona is similar to triangle CDB. They want to show that these two triangles are similar. What does it mean for two triangles to be similar? As of today, which is on the recording of this video, I have not taught proportionality and similarity yet, but I'm going to teach them in a few weeks' time. I'm going to make videos of them in 2 weeks' time, just looking for candidates that will watch me as I'm teaching them. So, if you want to show this, to show that two triangles are similar, you must show that the corresponding angles are equal, which is, you must show that the two triangles are equiangular, which is all of the corresponding angles are equal, or at least 2 of the corresponding angles are equal. You don't have to show all 3 of them. If you wanted to show 2 corresponding angles are equal, the third one will automatically follow from that. Right? The second way you can do that, you must show that the corresponding sides are in the same proportion, which is what we were proving on the first question, which is 10.1. At 10.1, we were given 2 equiangular triangles, and you had to show that the corresponding sides are in proportion. Right? So if you show all of the corresponding sides are in proportion, you have shown that the two triangles are similar. Or you can just show a minimum of 2 angles to be equal. Then you have shown that these two triangles are similar. So if you want to show that these two are similar, what you can do, you must show that maybe your angle F maybe of this triangle. Let's look at this triangle so that we can see which triangle we're talking about. This triangle FC Barcelona, FCB is this triangle over here. Let me make it red. So this triangle FC Barcelona is this triangle over here. And triangle what? And triangle CDB. And triangle CDB. So you're looking at this green triangle over here and this red triangle over here. So if you're saying triangle FCB is similar to triangle CDB, right? You can show that, which is your angle F of triangle FC Barcelona is equal to angle C of triangle CDB, which is F. Let's go to FC Barcelona and find angle F. So your FCB, right, which is your angle F2 over here. You must show that your angle F2 is equal to that angle C of the second triangle. The second triangle is the green triangle, which should be equal to C2 plus C3. So it should be equal to C2 plus C3. So, go to another angle. Maybe your angle C of the first triangle is equal to angle D of the second triangle. So your angle C of the red triangle, which is C1, angle C1 is equal to angle D of the second triangle, which is equal to angle D2. So if you've shown these two, that is enough to say the two triangles are similar, because you just have to show 2 corresponding angles are equal in measure, then you are done. Or, so you can show this, or maybe, or show that, let's say your angle F2 is equal to C2, C1, C2 plus C3, and maybe your B, angle B, which is angle B in this case, which is your B2, is equal to angle B of the second triangle, right, which is your B3. So you can show this or you can show that. As long as you show just any of the two corresponding angles over there, because you can show this is equal, this angle is equal to this, and this one is equal to this, or this is equal to this, and this is equal to this, or maybe this is equal to this, and this is equal to that. Any of the two is going to do the work. That's what it means. I'm explaining it this much because I haven't taught it yet, but if you watch my video that I will upload maybe in a few weeks' time, that will be having these proportionality and similarities, you will be fine. So in this case, what I'm going to do, I'm going to try to show that this F2 is equal to C2 and C3, and C1 is equal to D2. This will be enough to show that these two triangles are similar. So let's do that. So in this case, what I'm going to say, look, angle F2, right, is 90 degrees because we're told that BF is perpendicular to EC. We're given that in the statement, right? Because there is 9, so this is 9 as well. So let's go now. So I'm going to say now, I'm starting the real answer to the question. So I'm going to say the angle F2 is equal to 90 degrees. This was given, right? This angle F2 is equal to 90 degrees because our FB is perpendicular to EC. And then I'm trying to say F2 is equal to this C2 and C3. Where is C2 and C3? C2 and C3, we said this was 90 degrees as well. Why? Because it's an angle that is subtended by a diameter. So CD is our diameter. So we know diameters, they form 90-degree angles in the circumference. They subtend 90-degree angles in the circumference. So which is C2 and C3 are also 90 degrees as well. So we say angle C2 plus angle C3. They can make up 90 degrees. Why? Angle in semicircle. So it's an angle that is subtended in half a circle, which is an angle that is subtended by a diameter. And the angles subtended by diameters are 90-degree angles. So in that case, we can say therefore, our angle F2 is equal to C2 plus angle C3. Right? That's what, which is, we've shown this part. We've shown this part over here. Now we have to show that part as well. So, where is C1? C1 is this angle over here. Right? It's an angle between a tangent and a chord. Right? Remember, an angle between a tangent and a chord is equal to the angle that this chord subtends on the other side. So, your angle C1 is equal to angle D2. Why? Because of the tan chord theorem. Because the angle between the tangent and the chord is equal to the angle that this chord subtends on the other side. I did teach this on my bad actions. Go and watch it if you don't understand it on my playlists. So in this case, we can say, look, our angle C1 is equal to angle D2. Why? This is the tan chord theorem. Right? Because our tangent EC and our chord, or maybe, yeah, and our chord CD. So, therefore, triangle FC Barcelona is similar to triangle CDB. By what reason? By angle. So, these are equiangular triangles. So, this angle is this entire angle here, and this one is that one over there, and this one is that one over there. We're done. Yeah. We move to another question, which is 10.2.2. So, what are they saying? They're saying at 10.2.2, give a reason why G1 is equal to 90 degrees. So G1 is this angle over here. They're asking why it's 90 degrees. So look, the original diagram, I've drawn it in purple, right? All the green information, or the red one, is what I've added myself. So look at this 90 that I've placed here. It's red, it's not purple, which means it's what I've added to the diagram. It was not part of the given diagram, right? So they're asking why is this angle 90 degrees? When I started doing this question, I gave a reason why this is 90 degrees. Because I said that if you have a line from center to a midpoint of a chord, that line will be perpendicular to a chord. Line from center to midpoint chord is perpendicular to a chord. So a chord bisector from the center is perpendicular to a chord. That's why this is 90 degrees. Because we have a line from center perpendicular to a midpoint of a chord. Therefore, it should be perpendicular to a chord. So, why G1 is equal to 90 degrees? G1 is equal to 90 degrees. Why? Because we have a line. We have line from center to midpoint of a chord. That's it. We have line from center to midpoint of a chord. So it should be perpendicular to a chord. That's theorem 1b, if you watch my directions. So I'm done with this one. Now we move to the next question, which is 10.2.3. 10.2.3. What are they saying in 10.2.3? They are saying, prove with reasons that CG squared is equal to CG times DB, right? So they want us to prove with reason that CD squared is equal to CG times DB. So, in my experience with this topic, right, with similarity, so one of the ways, which is my opinion, the easier way to prove Pythagoras theorem is to use similarity, right? And yeah, we use similarity of triangles to prove Pythagoras theorem. I haven't done it yet, but I'm going to teach it as well. So when I see some sort of a CD squared and I have some similarity, that's the only thing that comes up to mind is the Pythagoras theorem. So the way in which I prove the Pythagoras theorem, it allows me to set up these things like the CD squares and stuff, right? No problem. So if you want something with a square, let's say you're working with similarity, look at this triangle here, right? Look at this triangle over here. These two similar triangles here. We have FCB and CDB. So if you look at both of them, there's two sides that is common in these two triangles. It's CB, CB, CB. So you can look at them, FCB, which is here is FCB, and look at the green triangles. So both of them, they're sharing that side. If you want to have something that has a square, so because we are trying to show, this is what we're trying to show. Trying to show that your CD squared is equal to CG times DB. So this is what we're trying to show. We're trying to show this, right? Your square of your CD is called CG times DB. That's what we're trying to show. In order to get some sort of a CD squared like this, the way in which you set up your similarity triangles, your CD should appear in both of those triangles. It should be a common side to those triangles of yours. Let me repeat this. If you want to have this CD squared like this, you must have two triangles that in which CD will appear twice on. I'm making an example. Look at these two triangles here. This triangle and that triangle. You have your FB, you have the CB here, and you have CB there as well. So with these two triangles, you can be able to find CB, or maybe the square of CB, because your CB appears in both of those triangles. How would you do that? This is an example. I'm going to write it with a different ink because it's just an example. Look, so these two are similar. If you take CB, you say CB, the CB, and divide by DB, is going to be equal to what? You see, because you want the square of CB, what is common, what appears twice. So you must set your ratios so that the CB appears twice as well. Because look, you said CB, this part over this part. But now you want to have this part, CB, which means you must take the ratio of FB, which is your FB in this case, which is this part over that CB. So if you cross multiply, you find that your CB squared is equal to DB times FB. See, you have something similar to this. So what I'm trying to say is that if you're trying to have a square like this one up here, you must set up the ratios of your similar triangles so that what you're interested in, the square of whatever that you're interested in, appears in both triangles. Look at CB and look at CB there. So I said this CB over this part, and because I want this part, so I must take FB. So if you want the square of CD, you must have a similar situation with two triangles in which CB will appear twice the same way, in which CD will appear twice the same way CB is appearing twice then. So I'm going to clean this part. This was just an example. So that's my experience with the Pythagoras theorem. So in this case, what I'm going to say is, listen, I want to have CD. Where is CD? CD is on this green triangle here, right? So this green triangle over here. Is there another triangle in which CD is in? Yes. CD is on this triangle over here, right? It's on this triangle over here. This is the only triangle? No. Even this triangle as well contains CD. But the triangles that I will be interested in are the similar ones, so that I can take the ratio that is similar to the one that I had here. So if I can have two similar triangles that share the side CD, I will be able to achieve this. But now if you look at these three triangles that contain CD, triangle number one is this one, CDB. You can say CDB contains CD because you want your CD. So your CD is on this triangle. Here is your CD. And this same CD is on this triangle as well, right? And it's on that triangle as well. So to me, it's easier to see that this triangle have a 90, and so is this one that have the CD. So you have two triangles, CDB, and this triangle here. They both of them contain 90, right? Then I can try to find another angle that will be equal, right? In this case, with this one and that one, right? It's obvious that this one, these two triangles, CDB and CDO, maybe, these two triangles, it's obvious that they share this angle over here. But I don't know which one of these, this one cannot be 90, and I don't know why I would say this one is 90. I don't have any reason. So I will struggle to show that these two triangles are similar. But I can see there's a 90 here on this purple triangle over here, and there's a 90 on this green triangle. There is it. Then I can try to find another angle that both of these two triangles will share. That will be equal, or not share, but that will be equal in both of them. So look, I will say this angle of yours here is this one over here, right? No problem. So I'm looking at this green triangle and the purple triangle, and then I can say this angle over here is the same as this angle over here, which is C3. So your D2 and C3 are equal because this side is equal to this side. These are radiuses, right? So the angles opposite equal sides of a triangle are equal. So if you look at this triangle now, we have an isosceles triangle. This side is equal to this side. So the angles opposite equal sides are going to be equal in length. So in that case, you have these 90 degrees that are equal, and you have these small angles that are equal. So you have at least two angles that are equal in measure, then the two triangles should be similar. So in that case, I'll say in triangle what? In triangle CDB and triangle. So I started on C, which is 90, and I go to the angle D that I think is going to be equal, and then went to C. So I'm going to go start at G as well, and the angle C3 that I think is going to be equal to D. So it's going to be G, CD. So the order is important. So I started angle G, I went to angle C, I went to D. So what I'm saying is this C of the green triangle is G of the purple triangle. So this C of the green triangle, this C2 and C3, I'm saying it's the same as G. And I'm saying angle D of the green triangle, which is D2, is the same as angle C of the small triangle, purple triangle, which is C3, which is what I'm trying to say. In that case, what I'm going to say, C2 plus C3 is equal to angle G2, and they're both equal to 90 degrees, right? We've already said that already. C2 and C3 is equal to 90, and G2 is equal to G1. G2 and G1 are equal as well, right? Did I not talk about them? No, I didn't. Okay, let me restart. Okay, I'll say in that case C2 plus C3, that is an angle that belongs to this triangle, it's equal to 90 degrees. Why? Angle in semicircle, which is it's an angle that is subtended by diameter. And I'm going to say angle F2 is equal to 90 degrees. Why? Slide from center to midpoint chord. Midpoint of a chord. That's it. So if this is 90 and this is 90, so therefore these two, which is your C2, angle C2 plus C3 is called angle F2. So which is these two angles are equal. Your C2 plus C3 is called angle F2. Right? No problem. What else do we do? So we'll say, okay, look, we have shown that this angle over here is equal to this angle over here. Now we need to show that these two angles are going to be equal, therefore we'll be done. So in that case, we'll say, okay, now, in triangle, let's look at in triangle OCD. In triangle OCD, or I'm going to say OC is equal to OD. These are radiuses, right? These are radiuses. So if your two radiuses are equal, which means you have an isosceles triangle there. So the base angles of an isosceles are equal. So the angles opposite equal sides of an isosceles are going to be equal. So in this case, we say therefore, your angle C3 is equal to angle D2. Why? These are angles opposite equal sides of a triangle. So they should be equal. So you have shown in this case that this angle over here is equal to that angle over there, and this angle over here is equal to this angle over there. Therefore, these two triangles are similar. Therefore, triangle FC Barcelona, no, triangle CDB is similar to triangle GCD. By what? By angle. So these are two equiangular triangles. These are angles with corresponding equal angles. These are triangles with corresponding equal angles. So in that case, look at CD. Here's your CD and there's your CD. That's what you're trying to show. So, but since it's appearing twice and they're similar, this is the best possible situation. So you say you want a CD. So this part, you say this part over this part is equal to you want your CD, which is that part, which is called this part over that part. So in that case, we're going to say CD over GC is equal to DB over CD. Why? These are corresponding ratios of similar triangles. It should be a triangle. So cross multiply here, your CD squared is equal to your GC times DB, which is what they wanted you to prove to begin with, which is this, which is that. So knowing how to prove the Pythagoras theorem makes this question very, very easy. So we are left with 10.2.4. I'm going to clean the board and then we're going to do 10.2.4. So let's clean the board and do 10.2.4. Okay, so now we're doing 10.2.4, which is the last question, question 10. So it is the continuation of this, and we have all this information from the previous questions. So what are they saying? They are saying, hence, prove that DB is equal to CG plus FB. So they want you to prove that, on the last question, that DB equals CG plus FB. This is what they want us to prove. That is what they want us to prove, right? So how do we go about this? Like I said on the previous question, when we were doing this, this was some sort of, it was easy for me to do it because I know the proof of the Pythagoras theorem, which I'm still going to prove, right? No problem. Then what we need to do now, they're saying show that DB is that. What is DB? DB is this length over here. This length over here. Which is, if you look at the green triangle, if you look at this green triangle over here, you can see the green triangle. So you can say that it's a hypotenuse of this green triangle. So knowing the Pythagoras theorem, you can say in triangle CDB, right? You can say your DB squared, which is this length, is equal to CD squared plus BC squared. This is Pythagoras, right? So your DB squared is equal to CD squared plus BC squared, which is this side squared is equal to CD squared and CB squared, which is that. So you know what this is. This is what you found here. Maybe you can try to find what this is. BC, or the square of BC. The square of BC, you can find it from what you prove on 10.2.1, because you can see that there's your BC, it appears twice and over there. So I said that if you can say this part over this part is equal to this part over that part, your CB will appear twice and you'll be able to replicate something like this. So we'll say, okay, CB over DB is equal to 1 this part, so it's going to be FB over CB. These are corresponding ratios of similar triangles, right? So cross multiply here, you can that your CB squared is equal to your DB times FB. So in that case, you have CD to be this, and you have FB, you have your BC squared to be this. So we said here, your DB squared is equal to CD squared. CD squared is what you have here, which is your CG times DB, right? Plus your CD squared. So this part is this. your base squared, which is this one, is dB plus your FB, right? In that case, you can see dB is a common factor here. So your dB squared is equal to your dB into CG plus FB, right? So in this case, you can divide dB both sides, dB, so in that case you have your dB equaling what? CG plus FB, which is what we're looking for. And I hope this question does make sense to you, as it does to me. Thank you for watching. I'm going to do another question paper now, which is May, June 2021 question paper, paper 2. So thank you for watching. Cheers.